Okay, so remember the idea of what we're trying to get through here is to basically give you guys an overview of how to collect data, which is what we did on Monday, right? How do you deal with the notebook? How do you type stuff in? That way you're recording everything you are doing in the lab, okay? Or actually, one of the three of you will be the recorder. Maybe you can take turns and stuff like that. But right, that's the idea where you have a way to record everything you do in the lab and collecting all the data. And now we're going to analyze it, right? We're going to have to. We have actually going to be 2 lectures on this because I'm not going to get through everything today. Okay, and this involves basically figuring out how to deal with the data once you have it in your Jupyter notebook. Okay, so the first question is, well, how do you get the data? So, and as usual, the picture sucks again. Make it smaller, make it bigger, and that makes it better. Okay, so the science data you're going to be collecting can either be collected by hand. That means someone is typing into the notebook or writing it down on a piece of paper as you collect the data, right? Or it could be generated by the experiment itself. So a lot of the experiment will generate computerized data. These are called data acquisition machines. So those of you who had electronics with me last semester know what those things are. If you don't worry about it. It's a thingy that basically converts, basically automatically collects the data for you, okay? And what I'm going to do is I'm going to show you, maybe like a manual example first, meaning like you're going to be doing an experiment, you're just collecting these numbers, okay? So like it doesn't even matter what these numbers mean, right? They're just numbers that you're collecting, maybe this is the I don't know, like the energy of a certain photon or something like that, okay? Right? And this is just an example of 20 numbers. So like I just, recorded 20 numbers. I actually have it automatically generated. But so you can put this in manually into Jupyter Notebook by just making a list of numbers. So this thing called data is a list, okay? And then equal. So equal doesn't mean equal in programming. What does it mean? Anyone know? Assignment, okay? It is assigning whatever is on the right-hand side to the stuff on the left-hand side. They are not equal to each other, okay? Because if you flip this doesn't work, okay? You cannot make data equal to a list of numbers, okay? You can make a list of number equal to data, okay? You see how that language doesn't make any sense, right, in English? So what you should think is you can assign the list of information on the right-hand side into a container called data. Okay, and then but if you say, oh, I'm gonna assign a container into a list of number, now the English doesn't make sense, right? Where the equal sign is symmetric, where assignment is not. Okay, right? I can assign a name to you guys, right? But your name is not you, right? So it doesn't work the other way. Does that make sense? So a lot of folks messes this up because you guys come from a lot of math, and this equal sign doesn't mean an equal sign, okay? All right, so once you have this kind of list of data in there, and feel free to just follow along. You can make up your own data if you want. It doesn't have to be 20 items long, okay? You can print out the data, okay? When you print out the data, well, you cannot print out the data because you have to run the previous cell. I did this on purpose, by the way. No, I'm just kidding. I didn't do it on purpose. Okay, you have to run the previous cell before you run to the next one. Okay, what I do is just do a shift enter, and note that these are code boxes, a code cell, not markdown cells anymore. Okay, and then you run the next one, and when you print it out, it just comes out like this. It's just a jumble of numbers, right? It's like, okay, that's, yeah. I mean, that verifies that, I typed the stuff in properly. What you can do is also get the length. The length is this len command, and then you put a parentheses. Whenever in Python, everything that's in the parentheses is known as a function. The way you want to think about function is that it's a machine that takes some input and gives you some output. Okay, the way I think about it is like a blender, right? If you put in a bunch of stuff in the blender, it gives you a smoothie, or it gives you, whatever, salsa, whatever you're making, right? So that's the idea. It's a machine that you have some input, it gives you some output, okay? So In this case, the input that you gave it is the data set, okay, that you just created, right? The output, okay, which we're printing out is 20. Why is it 20? Anyone want to venture a guess? Why does it say 20? Yes, Celia?
It's counting the numbers within your data set.
Yeah, it's just counting how many of these. So it's a little machine that counts how many elements are in your data set, okay? In fact, just to be a little bit more detailed, okay, it is this machine counts how many things there are in the first dimension of your data set. And then when we run into two-dimensional data sets, that's when you're going to see that as a slightly different thing. Okay? All right. You can also print out the type, meaning I'm going to do another resizing to make it. Doesn't this look weird to you? It doesn't like show up on. It seems like okay. Yeah, that looks nice now. Okay. You can also print out the data type. Okay. So in computer science in general, I think there's like many different data types. For us mere physicists, we just worry about like 3 different data types, basically. Integers, right? Real numbers, which are called float. Okay, it's a floating point number. So the idea is that you have a number, and this decimal can be actually moved wherever you want it to be moved. Okay, and then you have words, right? You know, 1, 2, well, not 1, 2, 3. You know, lights, projector, floor. You know, those are words. These are called string in programming. It's a string of characters. Okay, so when you print out the type, which is another machine, another blender, and you're shoving in the first element of your data, notice that the data actually starts counting from 0. So in all programming language, I think there's one example I can't remember. There's one wonky one where you start counting at 1. Everyone starts counting from 0 because it's past, I don't know, the 1600s when people figure out there's a number called 0 before. So you're giving it the first element, which is actually the list of data with a little bracket that allows you to grab just the first piece of that data type. So it's basically giving it 0.31 into here, right? And it's asking what type of data it is, and it prints out as float, okay? Because it's a floating point number. In other words, it's just a real number, okay? You can do complex number, and you can do like fancier numbers. You can make bigger floats, smaller floats, signed and unsigned integers as you like. But for now, just worry about these 3 types, okay? All right. So not only can you make a list of floating point numbers, of course you can make a list of character strings. So I can have a character string called apple, banana, cucumber. In order to put in these character strings, you have to put either double quotes or single quotes around them. Either way works, okay? And then you put that in this square bracket. So square brackets always indicate a list of stuff, okay? Round parentheses always represents function, and then we'll figure out what the other ones does, okay? All right, so this is a data string, okay? If I print out the data string, right? Well, you can see it on the bottom already. So it just kind of repeats it by itself. But now you have this, what's known as the memory of your computer, okay? All right, typing it up here doesn't do anything. It stores it as a text file, okay? But once you do a shift enter or push the little play button, now this information is stored into the memory. So data string, right, is now a container that has apple, banana, and cucumbers in it, okay? All right, and there are 3 things in here, right? So that's hopefully this is not too bad, okay? You can even mix data sets. Wait, where is it? Where's my mix data? Oh, before I mix anything, you can also add to the end of your list, okay? So in this case, there's a functionality called append, okay? And this is something that tricks a lot of people. This append function is a functionality of this container. So this container now has, you know, little buttons on it. You can do stuff to it. Like it's just a box, right? You want to open the box, close the box, but you can also add stuff to the box. When you push the append button, And you can append, durian, it's a fruit that starts with a D. That's what I was trying to figure out. Okay. Now, if you print everything out again, now this data string now has 4 things in it. Okay. And therefore, it has a length of 4, right? So this is the nice thing about lists. You can just append things to it very easily. Okay. We're going to see arrays, and it's going to be a little bit different. Okay. You can even mix stuff up. Okay. So data mix. So you can have integer, string, right? And you can mix the 2 up, and it's perfectly fine with it for lists. Okay. So I'm going to emphasize this list thing. This is a particular type of container that Python has. Okay.
In data mix, the data is the name of your box, your array.
Right. It's the name of the box. I made a box. I put a number 2 in it. I put an apple in it. I put a number 3 in it and a banana in it. And this is my box now. And then outside we'll say data mix. Okay. Okay. And this data mix thing has a functionality in the little button here. I want to add something to it. If I want to add something, I push the append button. Okay. Make sense? All right. Everything okay so far? All right. Even though maybe for a lot of you guys, this is a review, this is maybe a slightly different perspective, right, on how to picture these things, because it's kind of my own little wonky ways to understand things, okay? If you read the textbook, right, it's very technical. It's like, oh, this is this type, this is this type, blah, blah, blah. It's like, I just fall asleep, unfortunately, with that. Okay, so let's do something more interesting with the data. Okay, we can plot the data. In order to plot data, you have to have a plotting functionality. This is where this line here, this little green thing, is a special keyword, import. Okay, what you're doing is you're importing some functionality from a library. Okay, this library that we're gonna be importing from is called matplotlib. The reason it's called that is because basically Python stole all the plotting functionality from this software package called MATLAB, and then they just use it all. And then, and by the way, Python is free, and MATLAB is like like $50,000 per user per year or something like that. It's ridiculous. Okay, so basically you're able to use all the functionality of this plotting, at least the plotting part of MATLAB, without having to pay anything for it. Okay, specifically we're going to be using a Python plotting package inside there. So this is this is like all the functionality from MATLAB. Okay, but then this is the Python plotting part of it. It's a little piece of it that we're just grabbing. Okay, and what we're doing is we're going to use this as keyword to basically rename this whole thing as PLT, because I'm too lazy to type matplotlib pyplot every time. Okay, so I'm just going to call it PLT. If you're even lazier, you can call it P, but then you're going to run into trouble if you're going to declare a variable called P and stuff like that, right? PLT is pretty quick, like 3 letters, pretty decent. Okay, all right, and inside this pyplot package, now it's known as PLT. So this PLT has a plotting function. I can just say plot, and I give it the data, and I tell it how to plot things. In fact, what I'm going to do first time, I'm not even going to have that. Okay, and I'm going to comment, and I comment this out by just putting a little hashtag. Right, the first time I'm going to do it, right, it's going to draw it as a blue line at first. Okay, all right. In science, usually, at least the science I have seen so far, people like to see data in black dots because that's the one that shows up the most. Okay, and that's why I'm going to put an additional optional function into this little blender. I'm putting this, so this is a plotting blender, right? I'm giving it the data. I'm going to tell it also, oh, can you make the points black? K stands for black, because you can't use B because B stands for blue, right? And then I'm going to make them into dots instead by just typing a period there. You can make them stars, you can make them circles and stuff like that, but K dot will give you little dots. Okay, like, okay, you got a bunch of dots now on the screen. Okay, notice that it automatically made the vertical axis horizontal axis for me. Okay, it's a little weird because, right, well, let's think about this. Okay, so these are the numbers, right, I gave it. I'm going to print out the data so that you can see it right next to it. Okay, right? Those are the numbers, okay? These numbers correspond to which axis, the vertical or the horizontal axis? I'm going to scroll down so you can see the... So this goes from 0 to like 19 or something like that, right? And this goes from 0 to about 1. So what do you think these number represents? The vertical or the horizontal axis? Ooh, cool. Half and half. Let's fight it out. Okay? Who thinks it's vertical? And okay? Okay, most of you say vertical. Why do you think it's vertical?
Because the data set is within 0 to 1
Right.
versus the other axis is 0 to 20,
Yeah.
which is the amount of numbers that we have in the data set, but not the actual data set representations.
It's great. You should come up here and teach this, actually. That would be more fun. More fun for me, at least. So you guys hear that? So by just looking at the data, right? So the data looks like everything is less than 1, right? On the horizontal, there are numbers here that are bigger than 1 already. So that doesn't make sense already. Okay? All right? So the fact that the range of this plot, right, goes from 0 to 1, makes sense that amongst this data set, there's 0 to 1. All right? And Cecilia also highlighted another point. It's like there are 20 elements on here. And this is why it goes from 0 to 20 here. Because what it is doing is that it's going to take 0.3. I'm going to put it at the 0 on the horizontal, 0.3 on the vertical. The next point is going to be 0.84. Unfortunately, it's it's right here, around here, right? It doesn't have the little legend here. But so you see that? 1 corresponds to 0.84, and 2 corresponds to 0.9, 3 corresponds to 0.3, and so on, like that. It basically automatically made the x-axis for you, right? Okay. Okay. You can even plot mixtures. Oops, data mix not defined. I have to run everything. In fact, what I'm going to do is, this is a trick. Okay, so if you just run all cells, it'll just run everything so you don't run into those red boxes anymore. But then you have to go back all the way to the top. Don't worry, I'm not going to talk for 2 hours straight. I'm going to have you guys do stuff, okay? Okay, so I think we're here. You can even plot a mixed list. So if you plot the data mix, remember that was like some banana, some cucumbers and stuff like that. I don't remember what I put in the box. You can even plot mix. You can plot 2, right? 2, and there's a 3, and then there's an apple and a banana. Okay, but this doesn't make any sense, right? But you can plot them if you want. Okay, that's one cool thing about lists is that. So I'm going to keep saying this word list, and we're going to transition to array later. You're going to see why. Sometimes you want to use list, sometimes you just want to use array. A list has so much flexibility. You can shove whatever you want into it. It's like a carry-all box. Okay. Right. Okay. So why did I do this? You can plot the character lists. Okay. Why did I do it? Okay, so one of the things I noted down here is that be a little careful, right? So, 1 apple, 3 banana, that's not how you count, right? Usually. It's not alphabetical order, it's not any order. So when you have a list of stuff that are mixed, you basically cannot sort them. If you have a list of all strings, you can sort them alphabetically or reverse alphabetically, right? A list of numbers, you can sort them by value, right? But if you mix them up, you no longer have this sorting functionality, okay? All right. So so note that the data values on the y-axis, sorry, on the x-axis, the value on the x-axis, as Celia pointed out, is just a list from 0 to 19. Actually, it doesn't go up to 20, okay? Because, as always, in programming, you always counting from 0, right? If you count from 0 to 19, you get 20 things, right? Because you have to include the 0th element, okay? You can also explicitly put in both the x and y values, okay? So I'm going to shorten this so that we can see these numbers more easily. Okay, so I'm going to make my x value 1, 3, 5, 7, 9. Okay, just odd numbers, right? And then y value 1, 9, 25, 49, 81. Okay, and maybe some of you guys already see what the correlation is between these two numbers. Okay, two sets of numbers. Okay, so if you want to plot this, you put the x values first. Okay, previously, right, the first, if you only give it one list of numbers, it assumes that that's the y values. If you give it two sets of numbers, okay, it assumes that the first one is x, the second one is y. Okay, and then you can tell it to plot it as dots again. So that's what this looks like. Okay, right. So you have x values are, screw up. Right, x value starts at 1, and 1 corresponds to 1 here, right, on the vertical. And then 3 corresponds to 9. Let's go up to 9 and 81, 9 to 81. So they're, right, they're just putting, wherever these pairs are matched, they just put a dot, okay? That's all this functionality, that's all this little blender does for you. Okay. Before we move on, we also want to kind of be nice to our instructor and put labels on things. How come I can't scroll a little bit finer? There it goes. The scroller thing is back. Okay. We want to put labels, well, titles on the plot, and guess what the function, the little machine that does titles for you is going to be called? It's going to be called title, right? Okay. Title parentheses. You type in whatever in there, it'll make it the title. It'll put it on top of your plot, okay? And in scientific convention, you always talk about basically the dependent variable as a function of the independent variable, right? It's y versus x, right, all the time, okay? And then you can label the dependent variable axis. So in this case, y label equals area in centimeters square. So in this class, when you put units, just put a square bracket around it, okay? Notice that I even put in little dollar signs here. The dollar signs aren't showing up here. Why is that? Why aren't there dollar signs around my centimeters?
Because it's telling you, because the dollar sign is saying that it's a equation.
Right, it's switch it to a math function. So I'm typing in something mathy, I put dollar signs around it. The dollar signs doesn't show up, okay? In fact, what I want is basically centimeter square, right? It doesn't type centimeter little caret 2, it type in centimeter square for me, okay? So you can even use the LaTeX, this is the LaTeX equation functionality within your labeling, okay? So which was pretty cool about it, okay? All right, okay. And in fact, you can make these labels and titles either before or after you make the plot. It's kind of interesting that it does that for you, okay? Okay, let's see what we're going to talk about next, okay? So since this is a mathematical function, we want to do some sort of math stuff with it, all right? And in Python, a lot of mathematical function is inside this thing called numerical Python, okay? It's called NumPy, NumPy. Who call it NumPy, NumPy? NumPy, NumPy? Okay, I think people call it NumPy, okay? So, yeah, I think NumPy is cuter, but then NumPy. If you're at a job interview, you call it NumPy. If you're just talking to your friend, you call it NumPy. That's fine. Okay, so once again, this is another package from Python, right? That someone has wrote for us. Okay, and you want to import it, and I don't want to type NumPy all the time. Okay, so what I'm going to do is I'm going to shorthand it as NP, because I'm just lazy. NP, NP, NP. Okay, and these are conventional, shorthand that most people use. Okay, so in NumPy, instead of dealing with lists of numbers, it likes to deal with arrays. Okay, so what's the difference between a list of numbers and an array? Okay, an array is going to be a set of either integers, floating point. it cannot deal with strings. Okay, it doesn't deal with natural language. Okay, it only can deal with numbers. Because what's going to end up happening is that it can actually do like matrix multiplications and stuff like that. And I don't know how to matrix multiply bananas and apples. Okay, so neither does NumPy. So don't put stuff in there like that. Okay, so what I did here is I basically converted, right, these x vals that I defined up here, right? This is a list of numbers. I converted it into a NumPy array. And guess what the functionality is called? It's going to be called numpy.array. Okay. It like 99% of the stuff in Python makes sense. It's the 1% that gets you actually. Usually it's like, wait, that doesn't make any sense, and it doesn't. You can't figure out why. Okay. Basically, what happened is that you took a list of numbers. This is a list of like 5 numbers, right? And it basically converted it into an array for you. Okay. And I did the same thing with the y values. Okay. If I print out the same stuff, right? Now it has a little bracket around it. Okay. If I print out, I'm going to print out the stuff up here so you can see the difference. The x vals, right? Right. Okay. So there's comma stuff, right? And now you see there's a slight, it's a little bit different between them, right? You know, 1 dot, 3 dots. It doesn't have a comma between them, so this is a list will have all these commas. And the idea for these arrays is supposed to look like matrices. How many of you guys seen matrices before? Or vectors before? Right, hopefully everyone. Okay, it's supposed to kind of look like that instead. Okay, it looks more sciencey. Okay, let's just say that. Okay, all right, so this is the X array, right? Oops, what, yeah, X array. And in this print command, I'm going to show you guys, right? I can print out multiple things at the same on the same line. Because previously, what I did is I print the X and I print the Y. What happens is that they'll be on top of each other, one after another. But you can print them next to each other if you want, okay? By putting a comma in my little print blender, right? And therefore, I can print multiple things, okay? All right, you can calculate the length of these arrays just like a list, okay? But, right, when you print out the type of the stuff, now it's a float 64. Okay, that means it's a 64-bit float. Okay, what that means, if I have a marker, there are no markers in here, right? It can hold a number that has a precision of 202 to the 32, okay, with, you know, how many, you know, values it can hold, and it can figure out where the decimal is to the accuracy to 2 to the 32 also, something like that. Okay, it's a 64-bit floating point number. Okay, 32 plus 32 gives you 64. So I think it can go up to like, I don't remember, like 10 to the 32 or something like that. Probably not 10 to the 30, 10 to the 18 or something like that. Okay, because the powers of 2 doesn't actually goes up as the same rate as powers of 10s. Okay, so a little detail, but I doubt you will run into problems like this. But just to note that there is a limitation on how big of a floating point number and how negative a floating point number you can hold, okay? Or how close to 0 it can get. Okay. Okay, so appending, meaning, you know, you know, in the list it was nice. There was a little append functionality. On the box itself, remember when I wanted to add to a list, I push the append button on the list box, and then I can put stuff into it. Unfortunately, whoever programmed NumPy decided that this functionality should just be a NumPy functionality. So you can append to the array from NumPy append as opposed to, you know, if this was a list, I would just put X array big dot append instead, right? But in this, for NumPy arrays, you have to append with the NumPy functionality instead. So a lot of times you're going to end up typing NP a lot, because everything you want to do with the arrays, with other stuff that you're going to be doing with these, with numbers in it, you're going to be using the NumPy functionality, which is nice that it collects everything in the same place. But you also have to remember that, type NP. Whenever you're not sure how to do something with math, type np dot something and then you'll find it, okay? So what I'm doing here is I'm basically adding 11 to the X array and 121 to the Y array. And I think you guys are seeing why am I doing that, right? Why those values are connected to each other, okay? Right, so now, right, I started with 1, 3, 5, 7, 9, right? And I just added 11 to this, and I added 121 to the end of this, okay? All right. Okay. You can also print out specific parts of the array. So let's say I want to print out the 0th element, the 3rd element, or the tooth element. Okay. Okay. This is 1st, 2nd, 3rd, 4th, 5th, 6th, right? But then the accounting is 0, 1, 2, 3, 4, 5. Okay. So if I print out the 0th, I will get 1. Hopefully it's correct down here. If I print out 2, I will get 0, 1, 2. I will get 5 instead. Right, if I print out 4, I get 0, 1, 2, 3, 4. I get 9 instead. Okay? So you can grab a specific piece of the array. Okay? All right. I'm going to show you guys one more little thing. You can also print out a range within the array. Okay? And it's the same thing in a list, actually. Okay? So this is the colon syntax. Okay? So let's say I want to print out these middle, I want to throw away this number and this number. I only want the middle 4. Okay? Okay? What I do is I start with 1 because, right, 1 corresponds to 3. Okay? But I want to go up 1, 2, 3. I want the 4th one also, right? Guess what I type in here? 5. Okay, that's great. So these are, in math function, what do they call? Exclusive instead of inclusive, right? So remember in math, when you have a set of numbers that's like, you know, x is a set of number from 0 to 10, right? That means it doesn't include 10, it includes 0.999999999 forever, right? But if you write x equals to, you know, bracket 0, comma 10, then it does include that exact value 10, right? Okay, so Python is the mix of the two, is neither. Okay, it does the inclusive on the left-hand side, exclusive on the other side. Okay, it doesn't include the last one. Okay, and since these are integers for the indices, that will give us an error because I forgot the last parentheses. Okay, and so now it gives you those middle 4 numbers as we want. Okay, yeah, anyone question? Oh, okay. Okay. Now we're going to start dealing with for loops, and this usually trips a lot of students up. Because if you haven't done programming before, then that's like, what the hell are you doing? Okay, so you can automate grabbing some of these elements or automate doing a lot of repetitive tasks using these things called a loop. Specifically, the one I'm going to teach you is a for loop. So FOR is a keyword also. Okay, and so let's just look at what it's doing. Okay, so there's some FOR thing, and it's like Python crap. I don't understand what this means. But then below here, we know what print means, right? I'm printing x is equal to x, right? So it's going to print whatever x is. You know, maybe it's 1, maybe it's 3, maybe it's 5, maybe it's 7. Okay, and then I'm going to type x squared is equal to x star to star square. So when you want to do exponentials in Python, you do a star star. But if you want to do exponentials in Markdown, you do the dollar signs with the little carrots. Okay, different syntax. Okay, just to make you guys happy. Okay, to deal with 2 different syntaxes. Okay, so what is it doing? Okay, so it's printing 1, 3, 5, 7, 11, 9, 11, right? And then it's printing the square of it, hopefully, right? 3 square, 5 square, 7 square, 9 square, 11 square. So why did it do 6 things because I only typed this in once, right? Okay. So why is the number 6 special in this case? 6 is a special number for this particular array. Anyone on the right-hand side?
The amount of entries you have in the array.
Yes, the length of the array. Okay. Okay. So this is some funky language here, right? For x in x array big, what the hell is it saying? Okay. So the way you want to picture this is that if you find an eraser, right? Okay. So the x array, right, is a list of numbers 1, 3, 5, 7, 9, 11, right? The length of this is 6. Okay. So what it's doing is basically taking one of these, making it into just a regular x, okay? Do stuff, you know, put it in the blender, you know, and you know, make smoothies out of it, you know, compute x squared, for example, okay? Okay. Then it'll come back, and then it'll repeat the same thing, but instead the next time it'll put 3 in there instead, square it, okay? And then come back, it'll put 5 in there instead, square it, and then 7 square it, 9 square it, 11 square it, okay? So it's a little machinery that allows you to take basically one element at a time inside your array and do something to it, okay, until the end of that array, in this case, okay? I'm just taking a tea break. Okay. Does that make sense? How this allows you to do kind of like, if you're doing the same thing to every element on the list, you do a little for loop along that list, and it'll take one of these elements at a time and basically let you do something to it, okay? All right. Any questions on that? If there's no questions, I'll give you something even more confusing. Okay. All right. You don't have to loop through the elements themselves. You can also create what's known as an index for the elements. Okay. Notice up here, right? Up here, right? We have elements in X. We have elements in Y, right? We have 2 different arrays. Both of them have 6 elements, right? Same number of elements. And this will work as long as you have the same number of elements in each of your these arrays, okay? So instead of looping through each of the element, I'm going to loop through this character named I, okay? I don't know who I is. Yes. It's weird saying these things out loud. I don't know who I am, I guess. What I is, okay? But instead of in my little array of stuff, I'm putting this weird word called range 0, 6. Okay? In fact, what I'm going to do beforehand, I'm going to make a box beforehand so you can see what range 0, 6 is. Let's just call this test equal range 0, 6. Okay? And then print out tests. Don't do that. Let's get NumPy array. There it goes. Okay. Right. This thing called range 0, 6 gave me a list of numbers 0, 1, 2, 3, 4, 5. Okay. Why does it give me those 6 numbers?
They give you the starting point of the array and the ending.
Yeah, giving you the starting point 0, and then the exclusive ending point, which doesn't include 6 because 6 gets left out, and you end up with 5, right? One way you can think about this is that this is the starting point, and this is how many you want to count up to how many elements you want if you are counting by 1, okay? And range can also count by 2 if you want, right? Never close, okay? you can count by 2 by putting an extra comma. This is an extra option. So if you want to count by 2 instead, you put a 2 there. You want to count by 3. Range only works with integers. Okay, I'm going to show you the one that works with non-integer in a second. But so when you see this, right, instead of seeing range 0 to 6, I should not have removed the other one. Right. Instead of seeing range from 0 to 6, you should just see this list of numbers, okay? This is the same thing. You're giving it a list of numbers 0, 1, 2, 3, 4, 5, okay? But why do I want that, right? And why am I putting that, making that equals to I, okay? So this is, the I is basically an index for where I am in the array. Instead of looping through each of the elements of the array, I'm like looping through the address of the array. Okay, so now instead of printing the actual element itself, I'm going to print where it is in the element. So where that element is in that array. Okay, so I'm printing X array big bracket I, because that tells you, right, on the first time going through a loop, I will be equal to 0. So I'm basically printing array big 0, and then array big 0 square, and then also array big, sorry, y array big, right, 0, okay? So the x equals to 1, and then a square is equal to 1, and then y is equal to 1 because you square it. But then if you go down to maybe down here, 9, right? So x is, so 0, 0th loop, 1 loop, 2 loop, 3 loop. On the 4th loop, when I is equal to 4, right, it's gonna give me a 9 instead, because that's the 4th index element, okay? And then when you square that, you get 81, and of course the y always corresponds to the 81 value also. Okay. Any questions? Let's see. I'm trying to get to the stuff where I can stop talking, but we'll see. Okay. Okay, so what we're going to do next is that we have these two sets of numbers. I plotted them. And what I want to teach you guys is basically how to fit a curve through it. Okay? Okay. Does anyone already know what kind of curve will fit through this? Okay. It's not exponential. Just because it's going up doesn't mean it's exponential. You see the list of two numbers? 1 corresponds to 1, 3 corresponds to 9, 5 corresponds to 25. What does that look like? Right. It's a square function. Okay. I'm going to try to fit that to it. Okay. But before that, I want to kind of go through this little exercise in the Newman's textbook, which is actually a really cool exercise, because this actually happened. This is actually the discovery of the photoelectric effect, which won some unknown character some Nobel Prize. But what they did is they have an experiment where they shot light onto a piece of metal, okay? And depending on the energy of that light or photon that you're hitting it with, sometimes you would get no electron coming out of it, and sometimes you will, okay? And depending on how much energy is in that photon, you get a certain amount of kinetic energy electron that's coming out of it, okay? And this is what this is plotting, even though it's kind of like mysterious, okay? So x is basically the amount of energy of the photon that's coming in, and y is the amount of kinetic energy that's coming out by measuring the energy that comes out of the electron, okay? And so how many of you guys seen the photoelectric effect thing in modern, right? Remember that? You guys didn't? Okay, right? So the reason that the energy that comes out is not equal to the energy that comes in, because it takes a little bit of energy basically to ionize, meaning it's basically ripping an electron off a piece of metal and then shooting it into there. It takes a little bit of energy to do that, okay? And that energy is called the work function, and it's this crazy symbol called phi, okay? And I'm not going to go through all the math in this case, but I want to just kind of step you through it. I'm not even going to ask you guys to do this, but this is an extremely interesting little math they were able to do back in the late 1800s in order to do this because they didn't have computers to do this sort of stuff back then. But what they were able to do is basically compare this data, right? You have a bunch of dots, right? And they say, you can say, okay, how well does this line up to a straight line? The reason why this will line up with a straight line is because, right, the energy of the photon is connected to this x value. The kinetic energy is connected to this, right? So kinetic energy is a function of the energy of the photon, okay? And this m thing, okay, is basically conversion factor between that kinetic energy to, photon's energy to the kinetic energy. And basically this is a linear model because it basically follows the same format as y equals mx plus b, right? Okay. And you can actually make this fit by hand without any computer by following this little exercise in Newman. Okay. And yeah, so there's a bunch of calculations in here. I just want to motivate it. Okay. And what ends up happening is that you'll be able to calculate exactly what the slope and the y-intercept is for this particular data set without any computers. Okay, you can just do it by hand. Okay, and this is the equation for it. And the definition of EXY, EZ, EY, those are all defined up here. Okay, you can just compute those. Okay, so whenever you want to, if you're stuck on a deserted island and you don't have a computer and you need to make a linear regression, there you are. Okay, so know these, and this will save your life at some point, right? Okay. The reason I brought this up is also that, so in a linear fit function, right, a straight line meaning, right, okay, there are really two parameters, right? There's the slope and the y-intercept. And this can be completely determined on kind of this two-dimensional plane where maybe this is the slope and this is the y-intercept. And basically, there's a minimum point. Okay, this is going to be important for us to understand that since we're using computers now. There's a minimum point where you can compare this chi-square. It's basically comparing your fit data to your actual data. Okay, it's basically computing these distances, right, at every point and squaring them. The reason to square them is because you don't want the positive number to offset the negative number. So you square them to make everything positive. Okay? And that way, any data points that are far away from your line contributes a lot to your chi-square. Any data points that are very close to your line contributes very little. So if you're doing a fit, what do you guys think? Do you want a big chi-square or a little chi-square? A little chi-square, right? Because little means your data and your line are very close to each other. Okay? That's why this method is called chi-square minimization. So if you plotted the chi-square of the parameter b, meaning the y-intercept, as a function of, plotted the chi-square as a function of both the parameter b and the slope m, so just replace this with m, okay, you will kind of see this shape where it kind of bowls at the bottom at one point. Okay, this is known as a global minimum. Okay, because it's a linear function, it has one global minimum. And if you started off guessing at this point, what will happen is that, well, I got that wrong, and then you can actually compute a gradient to figure out which direction to go, and you can basically approach this point very quickly. Okay, but the functions you're going to be fitting in this class are not going to be straight lines. Maybe there'll be a few straight lines, so you can actually just use this equation. But there's more complicated functions to fit. Anything that's beyond just a straight line, what's going to happen is that this map of basically one parameter versus another parameter, and typically there'll be actually more, like 3 or 4 parameters. Okay, so you can't even draw it because we don't have four-dimensional vision, right? There'll be multiple global minima, multiple local minimas. Okay, and what's going to happen is that if you started off, let's say up here, right, you're going to travel down slope and you're actually going to hit this one. This is actually at the wrong minimum. Okay, And then if you start here, you're going to get to the wrong place. This is the actual real minimum that'll give you the best fit, right? So you actually have to kind of start off around that point. Because if you start around here or around here, you get to the wrong place. It's only around here that you can actually get to the right minimum, right? Okay, this is the global minimum. So when we're doing fits, what you actually have to do is kind of guess what these parameters A and B's are first, and you have to be kind of close to it before you even start the fit, okay? And we're going to see that, okay? All right, and this is where we're going to use this thing called SciPy minimize. I'm just checking ahead to see when I'm going to have you guys do stuff instead. Try it yourself. Okay, yeah. Oh, okay, I'm going to talk for a little bit longer then. Okay. All right, let's try to get through this, okay? So, so this is where we have this library. Once again, it's another library, kind of like SciPy, Matplotlib, right? Now it's called SciPy, Scientific Python. And we're going to use this thing called optimize inside there, okay? Optimize meaning basically optimizing so that you minimize this chi-square function that we're trying to figure out in order to minimize stuff, okay? So I'm going to import SciPy. I'm going to be lazy and call it SP, okay? I have the same data set as before. I'm just going to do the simple one, okay? I'm even, nice to my professors and put titles, labels, and plots and not have them take off points for me, okay? And then I plotted it, right? So, okay, same plots before, nothing changed yet, okay? So the physics model we're trying to emulate is that while, it looks like a square function, but the physics model is actually, well, let's say I measure the area of something. Sorry, I want to measure the area of something, right? You can actually calculate that from the lengths of two sides, okay? No, hopefully this physical model is familiar with everyone, okay? If you have a square, the length square will give you the area, okay? This is the model, okay? Oh, keep the models pretty simple, okay? I'm actually going to generalize this. Instead of just a square function, I'm going to allow it to have some parameter b, okay? Right? In this model, it should be pretty close to 1, right? Right, because there's a 1 in front here. So basically, my L becomes x, okay? And then while I'm going to have, it could have a linear part of it, cx, right? So this c parameter tells me if this actually fits to a straight line instead. And then d is basically a constant, so it actually fits to a flat line, okay? Okay. So I'm going to allow b, c, and d. So hopefully b will be close to 1, c will be close to 0, d will be close to 0, right? Okay. So when you're doing the fit, it's really important for you to know what these parameters are, and that way you can actually initialize it to the right place, because we're going to see that it will find the minimum very quickly. Okay. In order to model this, we have to define this as a function inside Python. Okay. The way we define a function in Python is def. Okay. So it's just shorthand for define. Okay. I'm going to call this poly2 because it's a second degree polynomial. Okay. The first thing it needs is a free parameter, meaning this is the variable you're going to run over. Okay. Okay. So x, that's the free parameter. It doesn't. You don't have to call it x. You can call it t, y, z, or whatever you want, but it has to be the first one. Okay. Right. And then the parameters are b, c, and d. Right. These corresponds to that. Okay. And then when I type in the equation to calculate the area, I better have it corresponding to the right thing. Okay, otherwise my fit will go to the wrong place, right? Okay. Okay. Now, so how this function works is that it'll take one number x, one number b, one number c, one number d, and it'll give you do some calculations, meaning bx squared plus cx plus d, assign that to be a, and then send it back to you. Basically, it'll send it back to you like this. Okay. Okay. It's a little blender that takes 4 numbers and gives you an area. Okay. Okay. So before we can do the fit, we're going to guess what these parameters are, right? Okay. I guess I already showed it to you guys. So I'm going to guess that b is equal to 1, c is equal to 0, d is equal to 0, right? Because that hopefully makes sense, right? Because this is just calculating the area of something. Okay, what I'm going to do is I'm going to fudge the number a little bit, okay? And that way it doesn't have a perfect fit, so I can show you guys the deviation. So instead of 121, I put 120, and then, I just mess with the numbers up on the area a little bit, okay? So it's not exactly what we have, okay? So if you run this, okay, so this is the initialization parameter. So, okay, so let me just go back up to this map, okay? I'm just keep harping on this, okay? So basically, that it has to be around here. So I'm going to guess somewhere around here. So that's what that param0 allows you to do. Okay, because if you guess somewhere around here, you're not going to get to the right spot, right? All right, and that's what this param0 allows you to do. Basically, initialize the parameters before you even do the fit. Okay, and guess what the curve fit function in optimize is called? Okay, it's called, well, curve fit. Okay. Okay. If I'm even lazier, I might even just call that SPO, but it's fine. Yeah. Okay. Anyway, so in order to do the fit, right, I give it the function I'm trying to fit to, this poly2 thing I just defined, right? The x value, the y value, just like when you're doing plot, right? You give it the x, you give it the y. Okay. And then you give it the initialization parameters. Okay. Because without that, it doesn't know how to do the fit. It doesn't even know where to start, right? Okay. So when you run this, okay, what it'll do is it'll pass back a array of numbers back to you. That's the fit parameters. That basically tells you what B, C, and D is. It'll also give you a matrix that's going to be n by n matrix. That's going to be the uncertainty. And we're going to deal with this later, but I want to focus on just this parameter fit. Okay? So this param fit, you don't have to call this. You can call it Bob if you want, right? But if you print this out, since we have 3 parameters in our function, it'll give you 3 numbers back. Okay? Okay? So, which of these is the parameters for B, for example? Anyone wants to guess? What's the B value? Just by printing this out. Someone read out that what's B equals to, which is basically the coefficient in front of the x squared. So, yeah.
The negative 0.139, etc.
Almost. Okay. So, remember when we
Sorry, it's the first one.
right, when we initialized, this is, so I tricked you guys, right? So A is the area, B is actually the coefficient in front of the x squared, right? So B is actually the first parameter, which I started off at 1, but it actually fitted to 1.02. So it's actually not exactly 1, okay? And that's probably because I kind of tweak around the numbers, okay? Okay. The second number here, negative, right, 0.14, right, corresponds to which term in my fit function? Right? It corresponds to this letter, right? This letter is actually negative 0.13, right? Sorry, 0.14, okay? And then D is 0.04, right? So these are close to 0, but not exactly 0, right? So since I kind of, messed up the numbers by changing it a little bit, I basically kind of made it a little bit of a linear function, right? Okay. Right. So how can we see this? Okay. How do we compare this to all these numbers I just printed out? Okay. What you can do is overlay the two together. Okay. In fact, I did it down here, and I'll show you guys how to do this in a second. Okay. Okay. So basically, what I did is I made a red line. That's the fit function, and I just drew the red line on top of the black dots. Okay, you can see that it doesn't fit exactly, right? So this is a little bit high. Sorry, the fit function is a little bit low. This is a little bit high. This is a little bit high, and so on, right? Okay, so how do I draw this nice, pretty plot for people to see? Okay, so going back up to the code, okay, right? So I was able to do the fit, right? Now I know what the parameters of this fit is. Basically, it's A equals to 1.02 times x squared minus 0.14 times x plus 0.04, okay? Okay. So now I have these parameters. What I'm going to do is I'm going to create a new set of numbers, okay? And I'm going to use this functionality called numpy A range. A stands for array range, as opposed to regular range, because I want them to have decimals, decimal numbers. I want them to be floating points, okay? So what it does is that it goes from 0 to 15 in increments of 0.1. So it starts at 0, 0.1, 0.2, 0.3, and so on like that until it gets to 15. So it's 150 numbers, okay? And generally, when you're making plots on a screen like this, couple of hundred data points is enough, okay? Don't do 3 billion data points because no one's going to see that anyway, because you can't really see it on the plot anyway, okay? Okay, so hopefully you guys can see this is just a long list of numbers going from 0 to 15, okay? What I'm going to do is I'm going to put these numbers into my second degree polynomial functionality, okay? So what's going to happen is that it's going to take 0, put it in here, okay, compute a y fit for me, take 0.1, put it in here, compute a y fit for me, 0.2, 0.4, so you see why automation is nice, right? But how does it know what what B, C, and D are? I also give it the parameters from each of the fit. So this is param fit 0, this is param fit 1, this is param fit 2. So basically these are constants that you're putting in there in order to calculate what the area, this A is, right, at every point on X. Does this make sense? How it's hiding a lot of automation behind it, but hopefully you can see how this is conceptually working. Okay. Right. Once I have this, right, what I can do is basically overlay the plot. Right. I can plot fit X and fit Y and put it on top of each other. Okay. And this is another reason why this function goes from 0 to 15. Right. Before it only went up from 0 to 11. Right. Now it goes up to 15 because, right, I made my X fit up to 15, right? Because if I've made it up to 20, it'll go up to 20. If it goes up to 100, it'll go to 100, right? All right, so how do I make it look pretty like this? And this is going to be required of you, right, to make your plot looks pretty, okay? So, well, first of all, you title, you label. This is stuff we already know how to do, okay? So, since it doesn't actually matter what order you do things in, okay? But, right, so the data, you always want to be in black points. So this is why when I plot X array, Y array, that's the data itself, right? The fit is the fit function. The data is just the array themselves, okay? I put the K dots, meaning I want a black dot at every point. I'm going to label that data, right? Hopefully that makes sense, okay? So this is just additional options you can put into this plot function, or the little blender. You just pushing the different buttons on it, right? You know, I want the label data button on that, right? Okay, right. That's going to make the black data plot, and then it's going to label it, but it's not going to do anything at that point yet. Okay. I'm also going to put the fit function that I fit it to, right, from just doing this calculation up here. So all these X value, Y values are already filled out just up here, right? Okay. I'm going to make that a line. A dash indicates a line. I think if you just put R, by default it does line, but explicitly if you want it to be a line, you just put dash, okay? And then you want a red line, R means red, okay? I'm going to label it fit equals to blah, 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 okay? It's going to show up here. For them to utilize the label, what you want to do is use this legend functionality. The legend functionality basically draws this box for you, okay? And I'll put red line means this, data means this. In fact, if I reverse the order of this, it'll probably reverse the order of this. I think typically you probably want to draw the data first and then the red line after. Make sense? All right. Okay, and then now I have all these B, C, and D here. How do I draw that? Okay, and this is a text functionality. Okay, so in order to draw this stuff, there's a text, and basically this is the position relative to, it's kind of like a fractional placement. Let's see if I can go up a little bit, right? So 0.1 means the x value, not on this x-axis, basically like fraction, like move 10% over on this plot and start typing b equals to, and this is where, if those of you not familiar with programming will be really confused by this, okay? I'm going to type in %.2f. What the hell is that? I don't see that here, right? Percent is like a little holder, okay? That tells you, okay, expect me to put in a number here instead, okay? That's going to be a floating point number that has two figures after the decimal. I can also put a number before here also, but I'm not going to do, okay? Right? Okay, what number should I expect? Well, the number you should expect is actually put another percent here without any, with just a space between them. Okay, param fit 0. Remember param fit 0 is that 1.02 blah blah number, right? So it's basically going to put 1.02 into here, and that's what comes out. Okay. Okay, in order to make this, 0.1, 0.8, by default, what Python does, it actually uses the coordinates of your x and y axis to place these things, which really annoys me because when the axis change, your stuff also change, right? So, so the thing you need to do is actually transform this thing from the trans axis instead of the regular axis. Don't worry about what all the stuff means. GCA means get current axes, but just copy this, okay, in order to make this work. Otherwise, it'll be in the weird place, okay? Okay, so I did this for B, C, and D. So whenever you have these fits, you put in these fit things. You also want to put the fit parameters on your plot. That way, someone can just look at the plot and say, okay, that makes sense, okay? All right. Okay, yeah, so now let's just a little bit of information, technical stuff, okay? So by default, well, in Python, when you're looking at a plot, you may not be realizing what you're actually looking at, okay? The whole thing is known as a figure, so everything you're looking at is part of a figure. In fact, you can run this command called GCF, it'll grab the entire figure for you. Okay, the figure is kind of like the canvas for the thing. It's kind of like the whiteboard. Okay. Okay. Inside a figure, inside this whiteboard, I can put axes. Okay. Axes are these lines, right? That allows you to basically, oh, what's 1, what's 2, what's 3, 4, 5, 6, 7, 8. And then the plot themselves are the dots or the lines. Okay. So there's 3 layers of stuff you're putting in here on top of each other in order to show these stuff, okay? Figure, axes, and plots, okay? So whenever you're dealing with, oh, how do I grab the, why would I care what the axes are? The axes basically tells you what the position is, kind of like the coordinate system on your board, okay? Where the plots are actually the dots that you're putting on there, okay? There's a little tutorial how to do multi-plots and stuff like that, and some of your lab will require this because you're going to have multiple plots next to each other, and so there's a little link to a tutorial there. Okay. So what we're going to do is that if we can, so everyone has their computer and their Jupyter Notebook open, right? If we can go and download this text file from Canvas and put it in the same folder as your Jupyter Notebook, okay? And what we're going to do is we're going to play around with this data set together, okay? All right. With that, I've been talking for more than an hour, so can we take, while you guys are doing that, can we come back at 3:20 and start again? Okay, so take a 7-minute break.